Okay, yeah, so we're happy to have Jason Alicea from Caltech presenting the JQI seminar today. So Jason is a leading condensed matter theorist. He's made many important contributions to the study of topological phases of matter, topological quantum computing, Majorana zero modes, parafermion zero modes, frustrated magnetism, and many other things. He I guess originally did his PhD with Matthew Fisher in Santa Barbara. He was a postdoc at Caltech, and then he was faculty at Irvine for a few years, and now he's faculty at Caltech. So that makes him one of the few physicists I know who's managed to stay in Southern California basically the entire time. Great to have you, Jason. So looking forward to your talk on internally engineered Majorana modes and twisted bilayer graphene.
All right, well, thanks for the very generous introduction, Mason. I really appreciate it, and very grateful for the opportunity to be here at, I think is the final JQI seminar of the season. So my talk will focus on twisted bilayer graphene, as Mason just said, which over the past couple of years has emerged as really a stunningly rich and tunable platform for strong interaction physics. So I'll be asking whether one can exploit that richness and tunability for applications involving fault-tolerant qubits. And along the way, I'll describe how we can use similar devices to the one I'm showing you here to partially unravel some of the outstanding mysteries of the twisted bilayer graphene phase diagram. So the work I'll be describing was done in collaboration with Caltech postdoc Alex Thompson, Ina Sorensen, and Esteban Najperge. Here's the reference, which actually just appeared, perfect timing, last night on the archive. So this talk, like much of what I do, is motivated by topological quantum computation. So to set the stage, I'll give a short overview of what that's all about. So in a nutshell, topological quantum computing seeks to build scalable, intrinsically fault-tolerant quantum computing hardware. And if you want to pursue that grand objective, the zeroth order thing you have to figure out is how to find topological phases of matter that host emergent particles called non-Abelian anyons. So non-Abelian anyons have all sorts of remarkable characteristics, one of which is that they carry exotic zero energy degrees of freedom. Those zero energy degrees of freedom span a very special kind of ground state degeneracy. So in particular, the degeneracy generated by a set of non-Abelian anyons consists of states that are all locally indistinguishable from one another. In other words, by performing local measurements of the system, either in the vicinity of the anyons or elsewhere, you can't actually get any information about which of the various degenerate states your system's actually populating. So that property makes this ground state subspace a particularly attractive place to encode quantum information. Essentially the same property that makes it difficult for an observer to decipher which state your system's actually populating also endows those qubits with intrinsic resilience against local environmental noise. Suppose next that you initialize your system into one of those degenerate ground states, which I'm going to call by a wave function psi sub I, and then take a pair of these non-Abelian anyons and adiabatically swap their position. Although these are indistinguishable quantum particles, that exchange transforms your quantum state in a very interesting way. So in particular, exchanging pairs of non-Abelian anyons generically rotates your system within this degenerate ground state manifold, and that rotation is quantified by a so-called braid matrix UIJ. All right, so that's the remarkable phenomenon of non-Abelian statistics. It's the most exotic kind of exchange statistics that nature in principle allows us to find. Now, from a quantum information standpoint, one can exploit non-Abelian statistics to implement a set of intrinsically fault-tolerant quantum gates. Essentially, you can think about these braid matrices UIJ as representing quantum gates acting on qubits encoded in this ground state subspace. Okay, so that in brief is the idea of topological quantum computation as envisioned by Alicea many years ago. Now, the billion-dollar question that the field has been wrestling with in the years since is how do you build the hardware to bring this beautiful idea to experimental life? Now, many years ago, Alicea also gave us an important hint for how to address that question by showing us the simplest possible phase of matter that harbors all of this interesting non-Abelian anyon physics that I just summarized on this slide. Okay, so in particular, the simplest platform that harbors non-abelian anyon physics by far, I believe, is a spinless one-dimensional superconductor. So if you take a system of spinless fermions, confine them to one dimension, and then gap them out by Cooper pairing, you will get an exotic topological superconducting state that is fully gapped in the interior, but supports so-called Majorana-zero modes, one at each boundary of the topological superconductor. So these Majorana-zero modes are the simplest kind of zero energy degree of freedom that non-abelian anyons carry. And so you can think about the endpoints of such a topological superconductor as representing non-abelian anyons that I reviewed on the last slide. So these Majorana-zero modes are described by operators gamma 1 and gamma 2. And those operators satisfy the properties shown in this box. So they're Hermitian, they square to 1, they have fermionic anti-commutation relations between each other, and importantly, those operators commute with the Hamiltonian. So in other words, gamma 1 and gamma 2, when you act on a state with either of those operators, you get a state with the same energy. So these properties collectively imply that the system has a ground state degeneracy. So you can do the bookkeeping for that ground state degeneracy by observing that each of these Majorana-zero modes is actually half of what you ordinarily think about as a fermion. So more precisely, by superimposing gamma 1 plus I gamma 2, you can define a single conventional fermionic two-level system that has an occupation number 0 or 1. Now, since these gammas commute with the Hamiltonian, this fermion operator also commutes with the Hamiltonian, which means in practice that you can add or remove a fermion from that F level without changing the system's energy. And therefore, there are two degenerate ground states associated with occupation number 0 and occupation number 1 for that fermion. Now, those states, as is the hallmark of non-abelian anyons, are locally indistinguishable from one another. You can understand that local indistinguishability in one of two ways. So first, from a formal standpoint, if you want to reveal the occupation of that F fermion, you have to do a non-local measurement that knows something simultaneously about gamma 1 and gamma 2, since F is inextricably linked to both of those zero mode operators. More physically, those two ground states arise from superconducting states that have either even number of electron or odd number of electron delocalized across the system. And so if you want to know which of those two states your system is populating, you essentially need to count up all the electrons in your system, divide by 2, and then you'll know whether you have even or odd number. And clearly that's not information that you can get by just performing a local measurement of your system. If you were to go a little bit further and imagine creating multiple Majorana-zero modes and using arrays of one-dimensional spinless superconductors, and then start swapping positions of Majorana-zero modes, then you will find that your system gets rotated within the corresponding locally indistinguishable ground state manifold, which is another hallmark of non-abelian anyons. Okay, so the model that Alicea came up with to describe this topological superconducting state is extraordinarily elegant. So I think you can literally understand all the properties of this slide and on the previous slide within almost a homework level of calculation. The problem, though, is that despite the simplicity and elegance of that theoretical model, finding practical realizations of spinless one-dimensional superconductors is not a trivial thing to do for two complementary reasons. First, there's the inconvenient fact that electrons carry spin. And second, among the thousands of superconductors that we now have access to, in almost every single case, the superconductivity arises from the formation of spin singlet Cooper pairs. In other words, both spin species are crucial for superconductivity in almost all known cases. And so there's obviously some tension between trying to do away with the spin degree of freedom and make a system superconducting. The good news is that in the last 10 to 15 years, people have introduced many ways of engineering topological superconductors of this type by combining judiciously well understood ingredients that are already widely available in the laboratory. I'm just going to describe one of these many proposals, which has been particularly influential and is due to the two groups shown down here, one from Maryland. So in particular, these authors taught us how one can use one-dimensional spin orbit coupled wires as a platform to engineer Majorana-zero modes. To illustrate how this idea works, let's begin thinking about the properties of such a one-dimensional wire without spin-orbit coupling. So if you ignore spin-orbit coupling, then the band structure for your wire is sketched here. So you just have spin-degenerate parabolas, one for spin up and one for spin down. If you turn on spin-orbit coupling, this band structure gets rearranged. So the spin-up parabola can shift rightwards, for instance, and the spin-down parabola can shift leftwards. So if you stare at this band structure, you can see it's still not quite what we want, because it doesn't matter where you situate your Fermi level here. You'll always be partially occupying both the spin up and spin down bands, whereas we're trying to get something which looks effectively spinless. So the beauty of this idea is that it's exceedingly easy to cure this problem. So this crossing here is protected by time reversal symmetry. And so if you want to lift this crossing, you can simply apply a magnetic field, which will open up a gap in the spectrum at 0 momentum. And now there's a sweet spot. So if you put your Fermi level within that field-induced gap, then your system has a single partially occupied band rather than two. And in this important sense, the system now appears as if it was described by spinless fermions. Crucially, however, if you look at the electrons at the right Fermi point and at the left Fermi point, there's a non-trivial spin structure that remains. So in particular, the electrons on the right side of the Fermi level, those are mostly spin up. Those have their spins mostly mostly pointing up because of spin orbit coupling. So the spins will be a bit canted to the rightwards, but again will be mostly aligned upwards. On the left side, those spins, again due to spin orbit coupling, will point mostly down. Again, a little bit canted by the field, but to a good approximation, these spins can still be mostly anti-parallel to one another. And this is a really crucial property because the fact that you have both spin up and spin down states available at the Fermi energy makes this wire very easy to gap out by superconductivity. So if you place this spin orbit coupled wire next to a garden variety spin singlet superconductor, there's a so-called proximity effect that takes place. Electrons from this wire can spend some time in the singlet superconductor and come back. In doing so, these electrons inherit the pairing that's native to that intrinsic superconductor. And the key thing is that since you have both spin up and spin down states available at the Fermi energy, that Cooper pairing can efficiently take place and gap out your wire. Okay, and once that system has been gapped out, you are basically done. You'll have Majorana zero modes, one at each end of the wire, provided your Fermi level sits within that field-induced gap. So it's a very beautiful idea for how to engineer a platform with Majorana zero modes. As you might expect, this proposal in short order generated a wave of experimental activity. Over the last decade, this experimental activity has taken place among groups all across the world. Here's two examples of devices that have been fabricated. This one by the Delft group, this one by Copenhagen group. Now, despite the decade of experimental activity that has taken place since, I think it's reasonable to say that there remains a spirited and not unreasonable debate as to the extent to which Majorana zero modes have actually been synthesized in these kind of devices. Now, I don't want to go into the details of that debate. Instead, I'd just like to comment briefly on some of the challenges that you might expect would need to be overcome in order to make a device like this actually work in practice. So one thing you might worry a bit about is the application of a magnetic field. Right? So that magnetic field, it was necessary in order to get this spinless regime, but at the same time, it's also detrimental to the formation of superconductivity and one of the key components of this device. And for this reason, there's been a variety of ideas over the last several years, which I think have become an increasing theme in the literature as of late, to figure out ways of getting the same basic outcome, but without the need to apply this external magnetic field, basically choosing some other source of time reversal symmetry breaking. So that's one thing you might want to do away with. A second thing that you might want to do away with is the need for this proximity effect that links very different kinds of materials. Right? So in this structure, we had a semiconducting wire, and we had to place it next to a superconductor, for instance, like aluminum or niobium or some other superconducting material. And the merger of those two very different kinds of systems opens up a whole can of worms. So there's lots of issues that can arise. For instance, the interface can be a source of disorder. There can be a large amount of charge transfer between the superconductor and the wire due to work function mismatch. And the presence of the superconductor can also, in principle, hamper your ability to gate tune this wire just due to not very interesting screening effects, which can hamper your ability to tune into the relevant regime that you need to get Majorana-zero mode. So with those challenges in mind, I'd like to now pivot to twisted bilayer graphene. And what I'll describe as the talk goes is a way that twisted bilayer graphene might be able to do away with both of those challenges. So in particular, I'll try to use twisted bilayer graphene to get Majorana-zero modes without ever invoking external superconductivity, external superconducting proximity effects with foreign materials. And if the stars align just right, we'll also be able to get Majorana-zero modes in that platform without the requirement of adding a magnetic field. All right, so maybe I should pause for questions if I'm kind of switching to a new phase of the talk. If there's any issues concerning the first part, I'd be happy to address them. And maybe I can reiterate. I very much question.
Actually, my question was about time reversal symmetry, and then the requirement of B. Probably once you show your proposal, then I will see why it's fundamentally required.
Unfortunately, I have a leaf blower that's I think being applied right outside my office right now, so I couldn't hear very well. But I think you asked why.
My question was that why fundamentally we need a magnetic field to break the time reversal symmetry to get the Majoranas, and probably your talk will address that.
Well, okay, so I can say two things, two related things. It's a good question. Thanks for asking. So first of all, if you want to get unpaired Majorana-zero modes at the endpoints of a superconducting wire, you have to break time reversal symmetry. That's absolute fact, because if you preserve time reversal symmetry, then Cramer's theorem would basically tell you that for every Majorana-zero mode you have at the end of your system, you have to have a partner Majorana-zero mode that transforms that transforms into each other with under time reversal symmetry. So time reversal symmetry breaking of some type is always necessary to get unpaired Majorana-zero modes. Now, the specific source of the magnetic field in this context, if I just back up a second, okay, so I wanted to basically lift this crossing. In order to lift this crossing, you need to be able to hybridize your spin up and spin down modes. And a magnetic field, let's say applied along the X direction, is a very efficient way to do that. And so the role of the magnetic field in this context is basically to hybridize those two modes. So you take that crossing and you transform it into an avoided crossing. So it's a mechanism for breaking time reversal symmetry, but it's not the only mechanism for breaking time reversal symmetry.
So, but if it's spontaneously broken through some exchange, let's say, then that's possible.
Yeah, certainly. Yeah, and one angle of attack that people have thought about recently is to couple a wire to a ferromagnetic material where time reversal is indeed broken spontaneously, and you rely on exchange interaction rather than an external applied magnetic field.
Thank you.
Okay, no problem. All right, so let's pivot now to twisted bilayer graphene. So starting from single layer graphene, single layer graphene is already a very interesting material. It has this famous band structure shown here, which supports a pair of massless Dirac cones, one at the so-called K point of the Brillouin zone and another at the K prime point of the Brillouin zone. To make twisted bilayer graphene, we have to introduce a second graphene sheet on top and then twist one layer relative to the other. So as twisting takes place, you can see this visually striking moire pattern appearing that arises from the rotation of those lattices relative to one another. I've stopped this rotation at a twist angle of 1 degree, which is very close to the so-called magic twist angle for twisted bilayer graphene. So sadly, despite the fact that I'm in my office, which should have ultra stable internet, I just got a warning that my internet connection is unstable. This happens from time to time. If there's any internet issues, please just flag them as soon as you can, and I'll pause and wait until this is fixed. All right, so at this 1 degree twist angle, which is again close to what people now call the magic twist angle, you can see that there's a new kind of superlattice structure that arises, which has this triangular pattern. And the corresponding moire unit cell is this triangle shown here. It's a giant unit cell. It's roughly 10 nanometers in size and contains thousands of atoms. Now at this so-called magic twist angle, the interplay between this moire periodicity and interlayer tunneling generates a really spectacular band structure for the system that features bands that are almost completely flat. Okay, so yet another inconvenience for the Zoom era. If I don't move enough, my light in my office will just turn off. So periodically I may have to wave my arms like an idiot to get the lights back on. So sorry about that. Okay. All right, so here I'm going to show you what that magic angle band structure looks like. So on this vertical axis, this will be the band energies as a function of momentum along various high symmetry cuts along the horizontal axis. And so I'll be using here the famous Bistritzer-McDonald model for twisted bilayer graphene from this PNAS paper. In this band structure that I'm showing you here, this corresponds to a twist angle of 1.5 degrees. So that's significantly above the so-called magic twist angle. And so I'm going to now play a movie that I owe to Alex Thompson for creating. That's going to show how these bands evolve as I decrease the twist angle from 1.5 degrees down to the magic angle. And the thing to pay attention to in particular are these bands that are colored blue. All right, so here's the movie with 1.4, 1.3, 1.2, 1.1, and finally the magic angle. All right, so we end up with these exquisitely flat bands as advertised that are separated by finite energy gaps away from the dispersive bands either above or below. Now in general, flat bands are pretty much universally interesting because they allow for interactions to dominate and which can often lead to spectacular new physics. Perhaps the most famous example is the quantum Hall problem. But here too, in twisted bilayer graphene, we'll see in a moment that interactions lead to spectacular departures from naive band theory predictions. Here's a zoom in of this magic angle band structure. So there's a conduction flat band and then there's a valence flat band. Crucially, both the conduction and valence flat band are each fourfold degenerate. This will be super important for things I say later on. So half that degeneracy comes from ordinary spin up, spin down degeneracy, and the other half comes from K and K prime valley degeneracy. So this part is probably clear. The valley degeneracy may be a little bit less so. So let me just take a moment to comment on that. So if you think about the original valleys of a single layer of graphene, we have K and K prime valleys, and electrons from, let's say, valley K in one layer can hybridize with the electrons from valley K in the other layer, and that produces its own set of flat bands. And similarly, electrons from valleys K, the K prime valleys from the two layers also hybridize with each other, producing their separate set of flat bands. Okay, so there's actually fourfold degeneracy here rather than just ordinary spin degeneracy. Here's a further zoom in of these bands. And so what you can see is that this conduction flat band and this valence flat band, they actually touch at a point. So they meet at massless Dirac points, which is reminiscent of what you find for ordinary single layer graphene. All right, so at this point, I'd like to sketch out what you would expect for the system from just naive band theory predictions. So suppose that you start with your chemical potential situated here between the flat bands and the adjacent dispersive bands on the bottom side. So in this case, your system just realizes a straightforward band insulator, so nothing surprising there. As you gate the system to start populating these flat bands, eventually, as the chemical potential rises, you'll start to populate some of these flat band states, taking your band insulator into a metal. And at some point, you hit the charge neutrality point at which the chemical potential slices these massless Dirac points. And then your system is just behaving like a semi-metal. Raising the chemical potential further, it takes that semi-metal back into a metal and eventually to a band insulator on the other side. All right, so based on that expectation, here's what you would expect from conductance, from the conductance as a function of carrier density as you make your way from band insulator to metal, to semi-metal, to metal, and then back to band insulator. Okay, so you'd expect some qualitative behavior of the conductance as shown in these kind of lobe-like patterns. Now, experiment gives us something which is vastly richer. So now I'm going to show you some experimental data from one of Pablo Herrero-Herrero's breakthrough 2018 Nature papers. There are two sets of transport curves here. So the red is at 0 magnetic field. The blue is at a small 0.4 Tesla magnetic field. The data, more or less follow what you would expect from this naive band theory predictions, but with lots of additional structure. So notice that there are these pronounced conductance minima at these highlighted density windows, which indicates the onset of insulators that are correlation driven. So despite the fact that you have partial flat band filling, there is evidently some kind of spontaneous symmetry breaking and some spontaneous band rearrangement that takes those metallic states and turns them into insulators. Okay, so we get these very striking correlation-driven insulating states. If you look at this red curve, actually adjacent to this correlation-driven insulator, there's actually a pronounced rise in the conductance on both sides. And that's a hint that this system is exhibiting superconductivity. All right, so here's a phase diagram as a function of temperature on the vertical axis, carrier density on the horizontal axis, basically just right within this density window here. And the resistance is shown in color. So these dark blue regions here and here are indeed indicating superconducting domes that are sitting adjacent to this central correlated insulator on the whole side. So these measurements have since been reproduced and extended by many groups around the world. I want to show you one other set of data from Efetop's group. It's a really beautiful set of measurements on what's believed to be, an ultra pure twisted bilayer graphene sample. And here one sees, correlated insulators all over the place. There's a very prominent correlated insulating state at charge neutrality, at quarter band filling, 3/4 band filling, half band filling. And one also sees superconducting domes basically interspersed throughout. So this is really just a spectacular gift from nature. We have this platform that we can readily gate tune between all sorts of completely different phases of matter. We can gate tune between band insulators, metallic states, various different kinds of correlated insulators, superconductors, all with a density change of a modest density of change of order 10 to the 12th per centimeter squared. And that tiny density change is really tied to the fact that the Moire unit cell in the system is just enormous. So that's why small density changes can have such a dramatic effect on the electronic properties of the system. All right, so armed with this gift that nature has given us, I think it's very interesting to ask whether you can exploit this richness and tunability for novel quantum devices. So there's various directions that one can take within that question. I will specifically ask whether we can make quantum devices that harbor Majorana zero modes. All right, so with that introduction, I can now give you the big picture, essentially the basic takeaway for the rest of the talk. Here's the device that I'll be describing more or less hereafter. There's one element here, this TMD, which I'm going to ask you to ignore for the moment. I'll say what that, I'll re-invoke that shortly, but for now, just suppose you have a system of twisted bilayer graphene that has a global backgate and a pair of independently tunable top gates. Okay, so that trio of gates allows us to independently tune the density and therefore the phases realized in this left region of the sample, the right region, and the central region in between. So I'm going to treat that central region in between as a gate-defined wire and try to understand the array of different kinds of phenomena that can be realized depending on what sits on the left and right side. So here's a simplified overhead view of that structure. So here's my gate-defined wire, and it's immersed between some bulk phase on the left and some bulk phase on the right. Now, the essential idea that I'll be bootstrapping off of is that electrons from this gate-defined wire, they can spend a little bit of time in each of the adjacent bulk phases. And in doing so, they can inherit the properties of those bulk phases via internal proximity effects. And so I will try to exploit those internal proximity effects for two purposes. So in the long run, I want to exploit those internal proximity effects for Majorana engineering. And then along the way, I'll describe how those internal proximity effects can be useful for obtaining electrical probes of symmetry breaking order that might be very, very difficult to detect using other techniques. All right, so that's a very zoomed out big picture set of takeaway messages. So now let me go through the details of how we can actually make these things happen. So let's start with the simplest scenario that you can imagine, namely where we have a gate-defined wire that's immersed between just trivial band insulators on the left and right-hand side. So we can arrange for this, this scenario by adjusting our trio of gates such that the chemical potential for each of those band insulators just sits below the bottom of the flat bands. So we're just in the gap between the flat bands and the adjacent dispersive bands. But the chemical potential for this central wire region will sit just above the band bottom for the flat bands. So we have some partial occupation of electronic states in the central region. All right, so here's where it becomes very important to recall that these flat bands have both spin and valley degeneracies. So recalling that there are spin and valley degeneracies, the generic gate-defined wire band structure that we have for this trivial wire case is shown here. So this is the energy versus momentum. So if I focus on these reddish curves, there are, these correspond to the states associated with valley K. And those are spin degenerate. So there's one parabola associated with valley K with spin up and another valley K set of states with spin down. So these blue guys over here, those are the corresponding states for valley K prime. Now this kind of looks a little bit reminiscent to the spin orbit coupled band structure that I showed you in the context of the semiconductor wire-based setup. But I want to emphasize that there's no spin orbit coupling shown whatsoever here. These states have trivial spin degeneracy, and the K and K prime states are just simply separated because basically rotation symmetry breaking in this wire geometry allows that separation to generically take place. There's no spin orbit coupling whatsoever here. All right, so thinking about the mission, I'd like to somehow craft a band structure for this gate-defined wire that has just a single partially occupied band. And so it looks like, I'm in bad shape here because wherever I put my Fermi level here, I actually have not one, but 4 partially occupied bands. And so the challenge for making a Majorana device here is that in order to get a spinless regime, we have to do 2 things. We have to figure out how to remove not only spin degeneracy, but also the valley degeneracy. So I'll address those 2 challenges one step at a time, beginning with spin degeneracy, and then I'll turn to the valley degeneracy part. Okay, so the root of the problem for spin is basically that twisted bilayer graphene is composed of carbon atoms. Carbon atoms are very light, and light atoms tend to have extremely weak spin orbit coupling. Right? So for all practical purposes, graphene, twisted bilayer graphene has 0 spin orbit coupling. Now we can, in order to lift the spin degeneracy, we have to figure out a way to force in spin orbit coupling into those graphene sheets. To this end, let me now tell you a little bit about a recent paper led by my colleague Stevan Nagy-Purgé, which studied twisted bilayer graphene adjacent to a tungsten diselenide substrate. So tungsten diselenide features heavy elements and has enormous spin orbit coupling. And one of the interesting results from this paper is that due to the hybridization between graphene electrons and that tungsten diselenide substrate, the twisted bilayer graphene inherited milli-electron volt scale spin orbit coupling. And we know this based on basically 2 complementary sets of measurements. First, we have indirect evidence of spin orbit coupling due to breaking of lambda level degeneracies that were resolved via STM. And more directly, resolved via transport. And more directly, a weak anti-localization kind of provides a definitive fingerprint of spin orbit coupling in the structure. Now that result is not at all surprising. There were many prior measurements of graphene-based setups adjacent to tungsten diselenide or some other transition metal dichalcogenide. And there's lots of precedent for expecting that indeed TBG, twisted bilayer graphene, would soak up some of that strong spin orbit coupling. What's less obvious is whether the rich phase diagram that I showed you before, that's characteristic of pure TBG, pure twisted bilayer graphene, survives the introduction of this material and the accompanying spin-orbit coupling. So there's two things you might worry about in this regard. One, you might worry about the possibility that this substrate just is a big source of disorder and mucks up your sample quality and to the point where a lot of this neat structure is just washed out. Second, you might worry that the generation of spin-orbit coupling has an adverse effect on the existence of, let's say, correlated insulators and superconductivity. All right, so the second interesting result from this paper is that the answer to this question is emphatically yes. The phase diagram retains all of its richness and in some sense more. Okay, so here's the phase diagram as a function of temperature and carrier density on the horizontal axis. Color, as usual, represents the resistance of the device. So this upper plot corresponds to a twist angle of 1 degree, roughly 1 degree, very close to the magic angle. And as expected from lots of other magic angle devices without tungsten diselenide, you see superconductivity, superconducting domes, evidence of correlated insulating states at partial band filling. And so indeed, lots of this richness is indeed survives. Interestingly, as you move away from the magic twist angle, there's a surprise actually. So here's a corresponding phase diagram for roughly 0.9 degree twist angle, and here's 0.8 degree twist angle. So by the time you get to 0.8 degree twist angles, all evidence of correlated insulating states have basically disappeared from the phase diagram, but nevertheless, superconductivity stays put. All right, so the upshot is that correlated insulators indeed continue to appear despite the presence of tungsten diselenide and the injection of spin-orbit coupling. And as far as superconductivity is concerned, superconductivity not only survives, but thrives in the presence of spin-orbit interaction. Okay, again, persisting down to significantly lower twist angles compared to what previous measurements have obtained. All right, so this is really neat. The upshot for what for the main purpose of my talk is that we now have a way of generating superconductivity. Generating spin-orbit coupling in twisted bilayer graphene via proximity effect with a transition metal dichalcogenide like tungsten diselenide. All right, so this will be the final setup that I'll be considering hereafter. So I'll have TBG adjacent to for instance, tungsten diselenide. And the sole purpose of this system here is to impart strong spin-orbit coupling to the TBG, to the twisted bilayer graphene layers. All right, so now let's revisit our trivial wire band structure, now in the presence of spin-orbit coupling. All right, so this is what I showed you before. So we had just trivial spin degeneracy associated with our blue and red bands. Once we introduce spin-orbit coupling, that degeneracy gets lifted, and your new band structure looks something like this. Right, so I have non-degenerate parabolas associated with value k, and instead of non-degenerate parabolas associated with value k prime. I can't really label these parabolas by spin any longer because of spin-orbit coupling. All I can say is that, let's say these k states are related to these k prime states by time reversal symmetry. All right, so we're halfway there. So now, if you think about putting your chemical potential, let's say down here, you have only 2 partially occupied bands rather than 4. And so, we've made some partial progress. Excuse me. Now, if you want to go all the way and get a spinless regime, what we need to do is figure out a way to lift these residual crossings in the spectrum. All right, so once we lift these crossings in the spectrum, then we can get a spinless regime, and then we'll be in business. Now, this is not a trivial thing to do. In order to open up this crossing, what you essentially need to do is figure out a way to coherently tunnel electrons from valley k into electrons in valley k prime. That requires a very large momentum transfer across the original graphene Brillouin zone. Alternatively, that kind of momentum transfer requires ultra short scale, angstrom scale modulations of the system. And again, that's not a straightforward thing to engender. So, when we were faced with this problem, we initially went down various false steps. We thought about, maybe you can somehow couple those values by a judicious orientation of the gate-defined wire. That turned out not to pan out. Maybe you can We also thought about introducing short-range scatterers, atomic scale impurities into that gate-defined wire, and that had other problems. And so I think, in hindsight, we were trying a little bit too hard to kind of force in this KK prime coherent intervalley tunneling. And it turns out a much better way to go is to kind of exploit, once again, the richness of the twisted bilayer graphene phase diagram and try to generate that KK prime coherent tunneling by exploiting internal proximity effects with certain kinds of correlated insulators. Naturally, theorists have spent a lot of time over the last couple of years thinking about the nature of correlated insulating states that have been observed in experiment. And here's a trio of papers that studied this problem and found that the correlated insulators that appear at charge neutrality and at half filling of the valence or conduction flat bands, these papers predicted that those insulators exhibit interaction-driven spontaneous intervalley coherence. In other words, these papers predict that you have spontaneous tunneling between electrons in valley K and electrons in valley K prime, which is exactly what we need in order to solve the problem I laid out on the previous slide. So interestingly, these intervalley coherent correlated insulators may also be the key to superconductivity, as was proposed by this neat paper by Essam Khalaf and company, who essentially described a route based on certain kind of topological defects in those intervalley coherent correlated insulators can naturally give rise to superconductivity in the adjacent density regions. All right, so with that, let's now think about our gate-defined wire, not immersed in band insulators, but rather immersed within intervalley coherent correlated insulating states. All right, so this, we now, by internal proximity effects, we now have a way of generating coherent tunneling between electrons in valley K and K prime, and which now gives us a mechanism by which these crossings can be lifted. Now, a technical point I should mention is that there's not a unique intervalley coherent correlated insulating state. There's a family of different kinds of intervalley coherent states that have subtly different order parameters with different spin structure. For instance, some of them might be spin singlets, some of them might be spin triplets. And depending on the details of the order parameter, these intervalley coherent insulators may or may not break time reversal symmetry. And it's hard to, rule out one over the other at this point, because the thing that distinguishes whether the order parameter, let's say, is a singlet or a triplet, arises from relatively small scale interaction effects and things like electron phonon coupling. So I'm going to consider both types of intervalley coherent correlated insulators, namely intervalley coherent states that break time reversal symmetry spontaneously and those that do not. Okay, so if this gate-defined wire sits between an intervalley coherent correlated insulator that spontaneously breaks time reversal symmetry, then your band structure appears as shown here. So these crossings are immediately lifted and one gets these nice sweet spots where if you situate your chemical potential in this gray region, for instance, you have a single partially occupied band. In this sense, your system appears now spinless. Now, if your order parameter actually preserves time reversal symmetry, then these crossings actually remain protected, not by valley conservation, but rather by time reversal symmetry, just because you need Cramer's degeneracy at these points. But it doesn't mean that we haven't gained anything, because the presence of coherent KK prime scattering allows these crossings to be lifted simply with the application of a magnetic field. Okay, so if you apply a magnetic field to the system, then these crossings can now be lifted, once again giving us a sweet spot of chemical potential where we have a single partially occupied band that looks like effectively spinless electrons. At
Jason,
this point, we're really...
Okay. Sorry, can I ask you a question?
Of course, yes.
Are you worried that, or should we be worried that the spin orbit coupling from the transition metal dicalcogenide will change the conclusion about this intervalley coherent correlated insulator?
Yes, you should worry about that.
Okay.
It's an excellent question. So if I go back here, these papers did not consider spin orbit coupling. It's maybe worth emphasizing that it was not a particularly close competition energetically albeit within, the Hartree-Fock treatments that were used here, between intervalley coherent correlated insulators and, the competitors. And so what you might hope is that there's some, reasonable stability window for introducing spin-orbit coupling. But, I'm pretty confident that if you make spin-orbit coupling too big, then you won't see, you probably would see a different kind of phase diagram entirely.
So I have a question kind of related to this as well. This is Colin Heikus. So there's a lot of interesting physics alone just in the dichalcogenide as well, right? Especially related to valley coherence, especially related to how magnetic field affects the bands of the dichalcogenide as well. Where are you living in the dichalcogenide band structure when you are at these chemical potentials in the graphene?
It's insulating, yeah. So there's no carriers descending from the TMD.
Okay.
We're just relying on kind of virtual processes where a graphene electron hops into the TMD, comes back, and then inherits spin orbit coupling.
But if you optically pump the TMD, can you do anything interesting in the graphene?
Maybe. I haven't thought about that, so I don't have anything concrete to say. But I think the problem would be much more complicated.
Yeah.
But sounds like an interesting direction. I don't think necessarily that you would be able to get, as far as I understand anyway, I don't think you would be able to generate the kind of KK prime tunneling that you would need. That might, let's say, provide a window for maybe imbalancing the KK prime energies. But we really don't want to imbalance those energies. We really want to keep them degenerate and just lift these crossings.
Okay, thanks.
Yeah, no problem. Yeah, so maybe just to reiterate what I was saying to Mason a second ago, we're considering a certain hierarchy of energy scales where the dominant energy scale is Coulomb by far, and we assume that Coulomb wants to generate intervalley coherent correlated insulators, and then we introduce perturbatively weak spin orbit coupling on top of that. And at least in the perturbative regime of spin orbit coupling, I think we're safe. You could imagine going away from that perturbative regime, in which case you should worry a little bit more. But that's the hierarchy of energy scales I'll be assuming. And the good news is that you should always be able to get weak spin orbit coupling by just by suitable design. Probably it's harder to get the strong spin orbit coupling, but we don't really want to be in that regime anyway. All right, so any more questions for now? Okay, so at this point, we figured out a way to get a band structure that hosts a spinless window of chemical potential. So we're really a stone's throw away from getting Majorana zero modes in this platform, but I want to just take a bit of a detour, a very brief detour, because the band structure that we've just obtained actually gives us a very appealing way of electrically detecting intervalley coherent order. And maybe I should preface this by saying that this spontaneous intervalley coherence that characterizes these intervalley coherent insulators, that generates translation symmetry breaking on the scale of the microscopic graphene lattice. So there's really ultra short scale modulation that accompanies the onset of intervalley coherence. And correspondingly, detecting that ultra short scale order directly is a not trivial thing to do. And so my claim is that by thinking about this gate-defined wire immersed between intervalley coherent insulators, we can promote that ultra short scale symmetry breaking order to large scale electrical signatures via the conductance of this wire. All right, so suppose that you measure the conductance as a function of chemical potential. All right, so the conductance as a function of chemical potential is shown by these blue curves down here for each of these corresponding band structures. Now, the key thing is that the onset of intervalley coherence generates a gap in the spectrum and can change the number of channels propagating through that wire from, let's say, 2 down to 1, and then back to 2 again. And that correspondingly generates a dip in the conductance, and that dip in the conductance is intimately tied to the onset of intervalley coherence. Because again, if you didn't have intervalley coherence, this band gap could not be opened. All right, so in the case where the IVC order breaks time versal symmetry spontaneously, even at zero magnetic field, you might hope to see this very non-monotonic conductance with, again, these dips signaling the intervalley coherence mediated band gaps. In the case where the IVC order preserves time reversal symmetry, then these band gaps should be opened in response to a magnetic field. Okay, so for instance, down here, if your common potential sits here, you have 2 channels. Up here, you have 1 channel, and that should manifest again as a conductance dip. And I think this is actually a very, very interesting experiment to try to set one's sights on in the near term, because if you successfully carry this out, it would give you, help to nail down the origin of correlated insulators in the phase diagram. And since these intervalley coherent states are potentially linked to the onset of superconductivity, you might even gain some insight onto the mechanism of Cooper pairing. Interestingly, experiments along these lines have actually already been done, not in twisted bilayer graphene, but in related contexts, namely in gate-defined semiconducting wires and just standalone semiconductor nanowires. And so in these semiconductor contexts, people, these 2 papers use similar ideas to basically electrically detect the onset of these so-called spin orbit gaps that arise from the interplay between spin orbit coupling and magnetic fields. All right, so we're basically proposing that one repeats these kind of experiments, but in the context of twisted bilayer graphene to shed light on the origin of correlated insulating states. All right, so finally, let me turn to internally engineered Majorana zero modes. In order to get a Majorana device, we can simply take the previous setup that I was focusing on, where I had intervalley coherent correlated insulators on both sides, and just replace one side with a superconductor. Right, so I just, very modestly gate tune the system on this right end from an intervalley coherent correlated insulator into a superconducting state. I should emphasize that we don't know very much about the nature of superconductivity. I'm going to assume that it's boring, fully gapped superconducting state that arises from the pairing of time reverse partners. But this doesn't need to be the case, but it's what I'll assume. All right, so within a phenomenological model that includes superconductivity and intervalley coherence, we can obtain the phase diagram for this gate-defined wire. So here's the phase diagram as a function of chemical potential and magnetic field. So I'll allow for the possibility of an applied magnetic field. This left phase diagram corresponds to the phase diagram in the situation where the intervalley coherent order breaks time reversal symmetry spontaneously. On the right-hand side, this is the case where time reversal is preserved at zero magnetic field. All right, so the key thing is that we see these topological phases in both phase diagrams, here, here, and here. Quite remarkably, in the situation where where time reversal symmetry is already broken by the intervalley coherent correlated insulator, these topological phases descend all the way down to zero magnetic field, which could give you an opportunity to obtain Majorana zero modes without even applying a magnetic field. If the intervalley coherent order preserves time reversal symmetry, you have to apply a magnetic field to get there, but nevertheless, it still persists. All right, so let me finish with a brief outlook. So these gate-defined wires in twisted bilayer graphene, I think, are really neat setups that provide a lot of, I hope, room for interesting future experiments. I described how one can use these gate-defined wires as an electrical diagnostic of ultra-short scale subtle symmetry breaking order. Detecting that symmetry breaking order can potentially shed light on the Cooper pairing mechanism in twisted bilayer graphene. And in the long run, I hope to have made a case that this seems like a promising platform for Majorana-based topological qubits. Now, there's various virtues of Majorana engineering in this platform that I wanted to comment on. First of all, these systems are exquisitely gate tunable. I think it's hard to overemphasize how useful that can be in practice. This setup does not rely on on external superconductivity, on external superconducting proximity effects with foreign materials. That's also hard to overemphasize. What a great simplification that could be for long-term device engineering. If the stars align, we can possibly get Majorana zero modes even at zero magnetic field. The exquisite gate tunability gives us the flexibility of real-time control over the patterning of phases within the device. These systems are amenable to various local and transport probes, which is, again, a really nice feature. You can do STM, you can do transport and various other kinds of measurements on these kinds of setups. And finally, thinking more long-term, these kind of systems are adaptable to mesoscopic geometries that would allow for a non-trivial qubit operation. On the challenging side, there's no free lunch as usual. There's certain things that one would have to wrestle with here, including the low critical temperatures for superconductivity in twisted bilayer graphenes on a couple of Kelvin scale. Disorder is a non-trivial issue, at least in present-day samples, and is tied to sample-to-sample variations in the phase diagram, which I think are not yet under good control. And finally, this whole proposal relies on the existence of intervalley coherent order, which is not yet confirmed experimentally. But again, these techniques should provide a way of testing for, of electrically testing for whether that order actually exists in experiment. In terms of future extensions, I think one of the most glaring and tempting extensions is to think about twisted trilayer graphene, which has also been shown to exhibit superconductivity and various correlated phases in the phase diagram. In this case, the critical temperature is higher and sustains actually superconductivity to quite large in-plane magnetic fields. And so that's a very tempting platform to think about similar ideas in. And more broadly, I think these gate-defined wire ideas could potentially be fruitful for both applications and diagnosing the phase diagram and other wiring materials. So that's all I wanted to say. So thank you very much for your attention, and I'd be very happy to answer any questions.
Thank you very much for the wonderful talk. So the floor is open for questions.
I have a question. Mm-hmm. So the superconductivity is 2D superconductivity, right?
Yeah.
So are you worried about like phase fluctuations being quite large for the 2D superconductor? And I don't know, what effect does that have on the Majoranas and so on?
I worried about this actually in different contexts a while ago, a couple of years ago now. And I concluded, well, I was convinced, I should say, that phase fluctuations in the 2D superconductor are not an issue. They play a similar role to phonons, essentially. They're bosonic order parameter fluctuations that spoil the effect to the same extent that phonons would spoil these effects, which I think is hopefully not at all. Now in 1D, I would worry much more severely, but fortunately, we're not going to enter the 1D superconductivity realm.
Can I ask a question?
Yeah, go ahead.
Okay. Hi, Jason. This is Yang Zhi. I have two questions actually. So the first one is I'm curious about how is the width of the wire compared to maybe coherence length of both of the order. And the second question is that I want to could you please comment on the superconductivity in the presence of spin-orbit coupling? Because the fact that it persists over a rather large angle, I mean like away from the major angle, that seems to suggest that it's different from the superconductivity in the major angle twisted bilayer graphene.
All right, so let me start with the first question, which I can't remember anymore. I'm sorry.
So the width of the wire.
Width of the wire, yes, thank you. Yeah, actually a very good question. And actually, if you look at this picture that I've shown you here, you might worry that, it looks like the width of the wire is maybe 5 graphene unit cells big, and an experimentalist would run away. This drawing is not to scale. Okay. So, the width of the wire we envision being, several, maybe order 10 moire unit cells. So that's a like 100 nanometer width. So
how does this compare to any of other length scale? I'm just curious about like what's the criteria?
Yeah, so the thing is, the width of the wire doesn't need to be small compared to, let's say, coherence lengths characterizing either of the adjacent phases. Presumably as you make the wire bigger and bigger, the problem gets more complicated because sorry, I have to wave my arms again like an idiot. Get my lights back on. Okay. Yeah, so first of all, you can start to generate more bands that are increasing the closely spaced, and that's that's not going to be good. That would just be a nuisance for the physics that we're actually trying to recover. But also, making the wire width bigger and bigger may make the fraction of time that the electrons spend in the adjacent region smaller and smaller, right? Because most of the wave function weight would be concentrated in the region in between. And so you don't want a too wide a wire simply to gain a good internal proximity effect. But there's not any sharp criterion that says if the wire width is larger than, let's say, a superconducting coherence length, that this physics doesn't work. And I think there's no limitation like that.
Okay.
The second question was about the interplay between superconductivity and spin-orbit coupling. I find it unlikely that spin-orbit coupling somehow qualitatively changes the mechanism of superconductivity in twisted bilayer graphene, simply because the critical temperatures and the location in the phase diagram at which the phases appear seems awfully similar with and without spin-orbit coupling. Why does it survive down to smaller twist angles? I have no idea. That might just tell you that somehow whatever spin-orbit coupling is doing, it's maybe promoting superconductivity beyond what you would get without spin-orbit coupling, without necessarily changing the mechanism. But I have no grounds for really quantifying that with any theory. But I think it's interesting.
Now if the spin-orbit coupling could mix the singly and triply channel, so that's why I'm worried about it. But you say that maybe in your proposal you only need a fully gap superconducting state. I forget what is the criteria for your superconductivity.
Well, actually, I think the mixture of singlet and triplet is a feature. It's not a bug. I think that's not a problem.
Okay.
And all I've assumed basically is that, actually, let me go back to the phase diagram. Sorry. Okay, so I've actually assumed a mixture of singlet and triplet pairing that the superconductor gives to the wire. And apart from that, I haven't really made any additional assumptions. I mean, these phase diagrams are extracted from some effective wire-only model, so we just need to inject some assumption about what superconductivity is doing. And that wire-only model really, I think all it requires is that that this superconductor is fully gapped, so that I could, in principle, integrate out those degrees of freedom to distill everything onto the wire itself. If it was gapless, then I think that's another place in which this whole story can crumble.
Mm-hmm. Okay, thank you.
Sure.
Oh, hi, Jason. Alicia, could I ask a question?
Yeah, go for it. Go for it.
Hi, Jason. Good to see you. Sorry, I probably missed part of your talk, actually, particularly the one. So the TMD, is there worry does that interfere with the Coulomb? Could it screen the Coulomb interaction needed for the IVC phase? Or
well, okay, so here's the actual experimental data for.
That's what I thought I missed. Okay, yeah, go on. I see.
Yeah,
so this is
there are correlated insulators, very commonly correlated insulators, basically, similar to what you find for.
I see.
TBD.
Okay, yeah. So right. So that's what I thought I missed. So could you break down the story about the disorder? I mean, so there are many sources of disorder here. So one I imagine is the angle. Presumably there is a twist angle disorder. And is the tunneling, the fact that you're getting spin orbit coupling from tunneling into tungsten diselenide and back, that presumably comes with some additional disorder, right?
What's the last thing you said?
The fact that you're tunneling into tungsten diselenide and back to get spin orbit coupling, that would come with some additional disorder from the alignment between tungsten diselenide and graphene. No, or
well, what I can say is that what Stevan's group believes, based on lots of measurements for these samples with and without tungsten diselenide, is that counterintuitively, this substrate, for whatever reason, actually improves device quality rather than hampers it. And maybe that's why superconductivity is persisting down to these low twist angles. I really don't know, but that's actually very reassuring that this is not a source of it's not hampering your device quality. It's actually seems to be doing the opposite.
Okay.
I don't have any deep reason to back that up. It's empirical observation.
I see. So I see. So and the device quality is based on like the superconductivity and also like generally like the quality of gaps and so on.
Yeah, I think part of it is let's say what the magnetotransport is another metric that I think is often used. The level of spectrum. I believe tends to be much more nicely resolved if I'm remembering correctly. With tungsten diselenide rather than without it.
I see.
So there's many metrics that seem to suggest that device quality is improving.
And is there a possibility of domains, etc., in this IVC order? That
Yes, I think the answer to that is yes. So actually, Alex had some discussion of this in the long supplementary material that she wrote. One kind of domain you might imagine is a domain between the order parameter here and here. That's a domain that we've kind of explicitly introduced. And so the assumption is basically that there's some kind of intervallic Josephson coupling. I'm not even sure if that's essential, to tell you the truth, but in fact, maybe it's even nicer if you do have some phase winding, because maybe that's a way of somehow breaking time reversal symmetry also.
Right. Well, I'm thinking about inadvertent domains across the IVC.
It could be the case, and I don't really, I can't rule that out.
So there's no, okay. All right, great, thanks. Yeah, it's nice, fun.